Okay, more electric potential and voltage. So I wanted to explain how we can know the direction of a electric field sometimes, even when we don't know its magnitude. So the key here is we have lines on these plots sometimes. Oh, come on. Where's the... There we go, finally. Okay, we have lines on these plots sometimes called equipotential lines. Okay, and these are what come out of your Excel spreadsheet. Okay, those, and the Excel spreadsheet you use to do the lab. So you can just, plot your 2D plots, and those lines on there are equipotential lines. And the equipotential lines connect points of the same electric potential. Okay, so connect points of the same electric potential. So you might, for example, have a little squiggle like this, and if it's a good plot, it will be labeled, and it'll say like voltage here is, I don't know, let's say 3.0 volts. Okay, now one thing that's handy to know is that field lines, which are lines that go in the direction of the electric field. Remember the field lines we drew? So there are lines, they have little arrows pointing the direction of the electric field. Field lines are always perpendicular to equipotential lines. So let me finish writing perpendicular to equipotential lines. Okay? And the reason why field lines are always perpendicular to equipotential lines is because field lines are always parallel to the electric field. So I'm going to say field lines and the electric field are always perpendicular to equipotential lines. Okay, now I want to prove that because we actually can. Okay, so I'm going to, erase that and make my little voltage, my equipotential line go like that, something like that. So we use the equation. I'm going to prove it here. Okay, so we use the equation delta V, okay, equals negative electric field dotted with delta R. So we go from one point to another, and we take the difference in voltage and the displacement, and that is related to the electric field like this. Okay, so what I'm going to do here is I'm going to take 2 points. Let's go baby blue. I'm going to take 2 points that are, actually let's not go baby blue, let's go green. Okay, well, I'm going to take 2 points that are on this equipotential line. Okay, so here's 1 point, here's another point. And my delta R vector goes from one to the other. So there we go. Okay, that's my delta R vector. These are both on the same equipotential line, which means they must have the same voltage, the same electric potential. That's the definition. All points on an equipotential line have the same electric potential. So delta V then must equal 0 because the voltage of these 2 points is the same. Okay, I've belabored that enough. So plugging those things in, we can see that, or plugging that one bit in, we can see that 0 equals negative electric field dotted with delta R. Okay? Now remember, this is only approximation. This is only an approximation unless the electric field is uniform, but it's a good approximation for a reasonably smooth electric field, and it's a better approximation. The approximation gets better the smaller delta R gets. So as you shrink delta R, down to be a shorter and shorter bit, this approximation gets better and better. Or sorry, this approximation gets better and better. So here, what we can see is that the dot product of the electric field and the displacement you go through is 0. If your voltage stays the same, the dot product of these two must be 0. Okay? The negative sign doesn't change things, of course, because negative 0 is 0. So we can actually just make that positive if we like. It doesn't matter. And so what this gets us, if we look at the interpretation of the dot product, some of you may already see, oh, that's the proof, I get it. But if you look at the interpretation of the dot product, you can see 0 is going to be the magnitude of the electric field, okay, times the magnitude of your delta R vector, okay, times the cosine of the angle between them, okay? So your electric field, let me draw this out here, your electric field here goes, say, like this, okay, and this angle here is theta. That's the angle between the electric field and delta R. Well, in order for this to be 0, in order for the whole thing here to be 0, one of these three terms must be 0. The E is not 0 because we're assuming there is some electric field here. The delta R isn't 0 because we picked delta R. You wouldn't pick a 0 displacement. That gives you nothing. So cosine theta must be 0. So cosine theta must be 0, which means theta must be a right angle. 90 degrees, pi over 2, whatever you want to call it. Which means then that if this here, this blue thing here is a right angle, the electric field must be perpendicular to delta R, and since delta R was 2 points on your equipotential line, when you shorten it down, it just points along your equipotential line. So therefore, the electric field, well, hold on, let me do a new page. So therefore, well, yeah, I guess whatever. I hate that. All right. Therefore, the electric field must be perpendicular to delta R. That's my little geometry class perpendicular sign, like the upside down T, you know. And since field lines are always parallel to the electric field, we then know that the field lines must be perpendicular to equipotential lines. Okay, so now I have prepared an example for us here. Well, sort of. First of all, this is a little sketch I drew of just a sort of a voltage problem. So if we want to find the electric field at points A and B, now I can't find the angles numerically, and obviously this is a crude drawing, but what I want to do first is sketch in field lines that go through points A and B. So they have to be perpendicular to the equipotential lines. The field lines have to be perpendicular to the equipotential lines, and field lines will always point from high voltage toward low voltage. That's something you should be able to satisfy yourself of. Look at the, whoops, oh come on, stop it. All right, if you look at the equation, okay, so I'm sketching this field line back from A, and then forward this way, and trying to, well, I've got a kitten climbing my chair, hold on. Okay, so I'm sketching it this way, and we have these two little kittens, and they're absolutely adorable, but they get into all kinds of trouble. Somebody's trying to climb the back of my chair, I think. Anyway, so these two here are field lines, and if you want to, you could sketch in more of them, just try to keep them perpendicular to the equipotential lines, something like that, and then maybe this one would, you'd have one going like that, something like that. You know, you can do all kinds of things. So, oh, hi. Hold on, just a minute. She's climbing. Oh, never mind. Now she's gone away. I just turned my head and found this beady little pair of eyes staring at me. So, now that we have the direction, let's look at what the electric field might be, or the magnitude of it. And I'm going to try to do that in this little pastel blue color. And so, let's say at point A here, we know the direction now has to be going this way, because it's got to be parallel to the fields. It's got to be going roughly that way. And then the magnitude of the electric field at A, so I'm going to say at A, magnitude of the electric field, okay, has to be equal to, well, so if you look at the, let me back up one and do a little something. So if you have delta V, okay, equals negative E dot delta R, then if delta R is parallel to the electric field, so this is the case where you know what direction the electric field is going, and you pick delta R to go parallel to it, then delta V, actually I should say this is if, okay, then the delta V is going to be negative, and when these two are parallel, the dot product of them is just their magnitudes multiplied, so it's negative E times the magnitude of your delta R vector. And so what you can get there is, geez, crazy, okay, electric field in that direction is negative change in voltage over change in position. This is provided you already know the direction, okay? Don't just go applying this willy-nilly. Understand how this applies. So in this case here, we already know the direction, so we can say this point here and this point here are the beginning and end of our delta R, and I'm guessing those two are like, well, this is delta R here. I'm going to just guess that those are 4 centimeters apart based on my horrible little hand-drawn scale. Okay, so let me actually take this and then we can say, so at point A, we're going to say delta R is 4 centimeters, and the change in voltage as we go from the sort of the uphill side to the downhill side, we have 30 volts here because see it's on this equipotential line. 30 volts here, and you go down to 20 volts there. So your delta V is negative 10 centimeters. Okay, so therefore the electric field, the magnitude of the electric field today, is going to be this delta V divided by this delta R, and so it's going to be negative. Whoops, sorry. Why did I write centimeters there? Volts. Okay, volts. So it's going to be, well, you're going to get a negative sign, but you want to make it positive because you're doing a magnitude. So 2.5 volts per centimeter, or if you really want to convert that, you can do it in 2,500. No, 250 volts per meter. But whatever. If we give you a plot that's labeled in centimeters and ask you to find an electric field, I think it's fine with all of your possible teachers if if you leave it as volts per centimeter. That's up to you. And then at B, at point B, my horrible handwriting here. This here, I'm going to say, I don't know. I'm just going to say 1 centimeter, okay? So delta R is, actually that should be just magnitudes of delta R, is 1 centimeter. So then your electric field magnitude at B is going to be roughly 10 volts per centimeter. So I hope that helps. And in the next video, I will try to explain how to do this when you don't know the direction already. So how you can find both components of the electric field if you don't know the direction already. All right, so stay tuned.